Thank you for joining me today here for Structural Modeling, an essential skill for engineers. My name is Deborah Brisbane, and I work here at RISA Technologies for almost about 4 years. And what we do, as Amber mentioned, we'll be focusing here on some tips that we have, some tricks about plate modeling, member modeling, and just overall modeling tips here for all types of models. So to start out here, let's kind of jump in, and everybody should be seeing my screen here. We're going to go through here a little bit more about the structural modeling process. Why is it more important to do structural modeling and as a process here, and why is it so important in getting your model correct? And one of the first things is that you want to make sure that your model is actually matches the as-built configurations of your building, or what your of your model. Not always building, actually, but any type of model, and that you get the loading correctly there. The as-builts are going to be really important that you have it inconsistent with what your structural model is. So you do want to continually make sure that as you go through the project, your model reflects any changes that happen along the way. Interdisciplinary models must contain relevant information, and that's one of the big pieces that when we start working with modeling, building information modeling, BIM, is becoming very popular, and there'll be different disciplines working in the same type of model. And so you need to make sure that everybody is coordinated during that process. And we're here going to be focusing on the structural models side of things, but you do need to make sure that as you go through the process, all the different types of models are actually containing the same information or relevant information. Some of the common pitfalls that we hit in structural modeling software is that there's a black box theory. So sometimes is when you're building a model, you've got all of your members in place, your geometry is set, but you get a result and you have a black box feel about it, where you get results that you don't quite not understand, or at least that there is what we have the idea of garbage in, garbage out. You build a model with inaccurate numbers on the front end, you're going to get inaccurate numbers on the back end, so your results are not going to be valid. So one of the things about structural modeling we're going to try to make sure is that we understand what we're building in the model so that we can understand the actual model results on the other side, and they're useful. We talk about here important things to make sure is that computer programs, here at RISA we're using computer software to do our modeling, but they don't have engineering judgment, okay? So it's the person who's driving that engineering software, that's the person who needs to make the judgment when building the model, as well as making the judgment when interpreting the results. So on both sides of that. And so you need to make sure that you think clearly about what you're building in your computer model. Non-experienced engineers do not have a feel for how structural will behave. So this is important that you note that you have experienced level people looking at the models as well as non-experienced engineers building these models, so that you have a level of confidence that you have sort of that rule of thumb. You understand what the model should be doing and understanding how it should behave, and then actually making sure that your model does behave that way. And you gain that experience as you go through the years, as you actually experience more and more structural modeling, but also in real life, seeing how things are working. So you want to make sure that you actually have somebody with experience actually understanding how that model is working too. Every person in your office can't know all aspects of the software. That was very true for me here when I started. I thought I was a RISA expert. I thought I knew everything that RISA 3D could do, and when I started working here, I realized there was just a world of things that the software could do that I didn't realize about. We offer we have other software as well. We have RISA Floor, RISA 3D, RISA Foundation, and whatever software package you happen to be using, it's important that you know that you get real good at the one you're familiar with, but that maybe you have somebody in your office who is an expert in another piece of software like RISA Foundation, and they might be a really good resource. If you find an expert in your office, maybe somebody who really excels in one package or one aspect of the software, that person can become your expert in your office, so you can always ask them questions about things that are going here. So, and I do recommend also training. The more and more you get to learn in things like webinars like today, but even in-person training, these things will help you become an expert in that software. Establish what information you want to transfer to your partners before starting your design. So that's important. I've talked to design firms where they have had full day meetings sitting down to understand about which piece of the information will be shared between the design partners. So the architect will hold the grid, while the engineer is going to hold the sizes of the shapes, and the electrical engineers are doing something here, HVAC, all the sorts of folks are coming around the table understanding who's going to contain and who's going to take ownership for what part of the project and what part of the design, and then making sure that your model represents that, so you don't step on anybody's toes along this design process. So we'll kind of dive a little bit more closely into the modeling and look at some more specifics of the models. So one of the things that comes up a lot in RISA 3D here is something called physical members. In this picture we can see here we've got a continuous girder. It's carrying some joists or some beams here, but it's going to happen with trusses. It's going to happen with continuous columns. One of the questions is, how do you model this? Do you draw it continuously from one node to the next, or do you draw it as segments? And it's kind of an older-fashioned way to do this. In older software, you would draw it more of a segment type. And we can see here in this picture that would be kind of option 1. You would draw them in as member 1, 2, 3, 4. You'll see here we would have drawn from node to node each member. And that is kind of what I will refer to as a segment design there. And that's a way to go. And you can, if you need this whole member to be pin, you would put pins at the end of member 1 and member 4 on the right here, and everything else would be fixed. So the member would be considered continuous, and then you would get member design on those individually. You still can do that in RISA 3D, but several years ago we came up with something called the physical member that shows you here in option 2 for the ability for you to draw from one end of the member all the way to the other end. So you're drawing a member continuously across. We're adding nodes in there, or joints along the distance of the member, but we don't need to break them up into separate members. Okay, so you just draw the physical element itself. And when we do it this way, there's going to be different considerations for both ways about what you have to maintain in order to have it broken up into pieces or as one continuous member. So if we look at the next one here, let's see how are these going to start to affect our design. So the first thing is our K factors. Okay, so your K factors is going to be your effective link factors, and they're going to be addressing here the column type buckling in our local axis. And one of the things is that RISA can automatically calculate those K factors for you. We're automatically calculating it for you if you want there. It's going to be based on the member sway condition and the end release configuration. And I'll show you that in a second here about how to do that when we jump into a model. But the program is going to be based on that for you. It'll do those calculations based on the AISC Chapter C table here. This should be a pretty familiar table from all of the different AISC books. You can find this kind of table here. And we're going to basically say, is it going to be fixed? Is it in a part of a sideways frame there? And what is the K value? Okay, so automatically RISA will do this for you if you request it. If you don't request that, we're going to default the K value to 1.0. So it will be at continually at 1.0. But if we see here, what happens when we do these modelings in these two different methods, a segmented method here, or if we do it as a continuous member. So on the left we see we're just using that physical member, and we're just having it continuous there, pin. Both of these columns are pin. On the right we added those nodes in, and these would have been a segment. So we're looking at it as pieces rather than the entire physical member. So when the program goes in to design these, we have to make sure that the program is actually looking at what are the end conditions. Are they pin, and are they for a segment or in each member? And when we do it as the segment method, we're going to see here if we have the computer as RISA 3D actually calculate it for us, we're going to see that we're going to get kind of different values popping up along the distance. We're getting 0.8 here because it's a pin fix. We have a fix in this segment, and then fix pin here. So we're going to see different values popping up there. And on the continuous one here that's pin, we're going to see the 1.0, which is kind of what we were anticipating to see along the distance. So when you do break it up into segments, you're going to have to go in and just adjust those values to be 1.0. Not a big deal, but something you want to consider. The other thing that we can have to consider is unbraced length. This is kind of a little bit more, gets in more and more involved here as you think about unbraced length. You're always going to have to address the unbraced length for any type of member, but when you split it up to a segment versus a continuous member, it's thought about a little bit differently. So for unbraced length, the default of the unbraced length is going to be the full length of the member. So when we look at it for right now, if we looked at the unbraced length of member 1, it would be the full length of that. On the reverse of that, when we do segments, the unbraced length would be defaulted to the smaller segments. So if we actually are not bracing that member at these nodes here, we would have to go in and adjust it to be the full distance from the corner here of M1 all the way to M4 at the top there. So that would be something you'd adjust in either direction. RISA can automatically calculate the brace points for you using segment command. So when you're using a physical member, which is the one down on the bottom here, this M1 full length, what we can do here is automatically RISA can calculate that as a segment. So wherever you have a node located, that you will be telling the program that is a brace point. So if we have oddly spaced nodes, things like that, or even if this was on a slope, like we'll look on a truss, the program will actually calculate that distance there along there. Wherever we hit a node, that'll be the segment point. And we'll take a look at that on a truss when we get to that there. Or you can manually enter in your unbraced length. So that's something you can tell the program that for maybe purlins, for example, that are not on nodes there, they're coming in at 4 foot on center or 2 foot on center. We can adjust that to be just exactly what we want it to be as unbraced length of 2 feet. So where do we do this? We enter the unbraced length into the member. We can double-click on the member. We'll get the Design tab listed up here, okay? And we'll see right on, this is your member dialog. It's going to come up, and there's a tab there called Design. And what you can do is the first there, the LBYY and the LBZZ will be addressing the column type buckling about the local axes, okay? And that's about those axes, so it's about the local YY axis and about the local Z, okay? So you're going to be bending about those. And the next one here you can do is going to be the flange buckling due to flexure relative to the top or the bottom of the member. So we call that L-comp top and L-comp bottom. Okay, you've got that listed right there. Now the first question I always have, and I think I have a couple slides jumped ahead here, I'm going to show you real fast, is what is the top of the member? The top of the member for me is always a question and that's based on its local axis. Okay, so when we look at the local axis of a member, we can see here that the top flange has a y-axis pointing up, and that would be the top of that member. The bottom is going to be just facing away from that. Okay, so when we look at a member and we're looking at design, what it's really important to do to understand where you're going to have your L-comp top and your L-comp bottom is to display your local axis, so you understand where your actual L-comp top is pointing. We can also see when we draw in members in RISA 3D that we're going to be defaulting here to have our strong axis here pointing up like we have it here, okay? But it is based on our local coordinates. So when we draw in the program, we can actually see that we're having a default to where we actually have our local coordinates with our y-axis up. And then the big important point is what happens when you rotate the member about its axis. What is happening on that local axis? Because not always are we going to have a simple wide flange with the y-axis is pointing up. We're going to actually have different situations. So if you actually have a rotation there, what you can see is that in RISA 3D, when we rotate 90 degrees, the axis goes with it. So the local y-axis follows with the top of the member. So you'll never really get disjointed about where that local y-axis is because it's always going to be following that strong axis there. So you'll always be in the 90 degrees, okay, when you rotate that. But some other software, just to kind of point out what some other folks do to make sure you understand for when you're using other software, you can see that it's not going to be, it might not follow that. You might have the y-axis being just now downward after a 90 degrees rotation, and the z-axis stays there. So it is important to make note of how your actual rotation is making a difference in your actual rotation and how your local axis displays. I'm going to pop back into that last slide here for a second here. So one of the things that why do we care about the unbraced length? It's important to make sure that we note it is important for unbraced length because of axial design. Okay, we talked about the K value is right there. The L here is going to be, so it's KL over R. Your L value there is going to be the unbraced length that we've just been discussing. So that axial design is going to be really based heavily on this unbraced length and the K values that we just discussed. So if you don't get those right, you're not going to get axial values, axial design that makes sense. sense. The bending design results also are going to be based on those L-comp top and L-comp bottom. So we have to define that exactly the same unbraced location there, L-comp top and L-comp bottom. We talk about where the top and the bottom of the member are. And we can see in this picture at the bottom here that we have a local axis displayed Y vertical. Okay, Z is coming out of the page and the X is along the distance of that. And that's going to be the default when we draw a member in RISA 3D. Okay, we'll pump through here a little bit. So let's talk about specific connections, just so we can visualize this. This is a really good thing to think about. Make sure you understand it and just think through it. So when we look at this standard wide flange connection, we have it coming into the center here. We have the top flange. We would say to ourselves, this is sort of an L-comp, top, bottom. We're asking questions about what is connected and what is not. So is the top flange connected in this picture? And that would be no. The top flange is not connected, so we would not be bracing the top flange. And the bottom flange is not either in this picture. So we are just doing a clip here. We're not actually attaching to the top or the bottom. The weak axis would be actually braced by this actual beam coming in, so we would have that, and the strong axis would not be being braced in this picture. Okay, so the second picture is a kind of a more typical floor framing, where you would think of how RISA floor might handle something like this, typically where you have a beam framing to the top of the actual girder. And in this one here, we can see the top flange is being braced. Okay, we're going to be bracing that in that connection. We're going to do the bottom flange is not going to be braced. The weak axis, yes, would be braced in this one, and the strong axis would not be braced, so we would not be bracing it in that direction. In this one, we see here that we're now bracing the top flange and the bottom flange together because we've got this blocking here, so we're actually going to be bracing this on the other side. So we not only are connecting with the beam here, we have bracing on this side, so we're bracing both top and bottom flanges here. We've got the weak axis being braced, just like we saw when the beam was framing in, and we have the strong axis still not being braced. Okay, so those are kind of some three typical connection types that you can think to yourself and then figure out how often. So when we say yes, they're being braced, well, how often are they being braced? So that would be a number that you would be putting in there. Now also construction type is really going to affect your unbraced length if we look at more of beams and how they're actually framed in with the deck. And this is kind of an idea of a composite deck framing into the beam there. And so what you see there is you've got your deck bracing the top flange, and this probably picture would be maybe your deck would be running the other direction, so you wouldn't be looking at it in this direction. But you get the idea is that actual deck there is stiff enough that it's going to help brace your top flange. The bottom flange is not going to be braced. Okay, there's nothing actually framing into the bottom flange on this picture. The weak axis is a question mark, yes. So I guess the question mark really reminds things to yourself, well, that weak axis is not being braced right now in this picture evidently, but if this is a 6-inch beam and this is like a 4-inch of depth for your deck and your concrete slab, then maybe it starts to help really brace your weak axis. But in this picture where this is real deep and then we've got sort of a small little topping on this, it probably is not bracing it there, okay? But that would be something you'd want to sort of address, and if you need that bracing, maybe you start to worry about different things to help brace that weak axis. Strong axis here, we say no, it's not going to be bracing our strong axis. But again, if this becomes so deep, there'd be questions maybe that beam is not quite being braced there anymore either. Okay, so the same thing here if we just do metal decking. Again, metal decking, is the top flange helping to brace that or not? So if it's just in this picture looks like just a simple metal deck on a pretty large girder, then probably not. The stiffness of that is probably not stiff enough. But if you detail it in a way that maybe you help put yourself a plate down there and you weld it, you're doing some sort of welding to help connect it to the top flange better, then maybe you start to actually get some top flange so that it is being braced up there. But in this simple bracing frame here where we see nothing on the bottom, the weak axis or the strong axis, nothing, we would just be saying no in this. Okay, so we've got a lot of different situations, and you're really going to, most times, look at how you're detailing it out to understand really if it's being braced or not. And of course, if you don't know the answers, things like that, maybe you go conservative, and then as you need it more and more, you might try to go in and detail it so that you can get some of that bracing in there. Okay, so let's jump into RISA 3D for a second to kind of take a look at what, as we talked about this a little bit. One of the things that's nice is kind of as we talked about just single stick framing, it was simplistic, but a truss is a really good way to understand this. So if we look at this truss on RISA 3D, I kind of built it two different ways. The bottom truss here shows us a continuous member drawn from one node to the other, and so this is one long continuous top chord and bottom chord. And then on the top we see here that we've got the segments, okay? And one of the things that we looked at here is if I double click on this member, that's our top chord. We see our general properties, but I can jump over to the design tab. And what I might do in here is our LBYY. So our LBYY on this member here is going to be maybe 4 feet for a purlin spacing of 4 feet. And to better explain to you what I mean by LBYY and LBZZ, I'm going to display my local axes so you can see that. So if I go to plot options, I can open up my plot options and open up my member display. And under wireframe there, I see that I have a local axis display. So I can turn on my wireframe local axis, and I can say OK, and all of a sudden I get now local axes all over my screen. One of the things that I did in particular is that I drew consistently from left to right, so that I did see local axes all in the same direction. Okay, if you start drawing things willy-nilly all over the place, you're going to start getting local axes in different directions, and it can get distracting on how to actually do this unbraced length. So a very good rule of thumb is to just try to stay consistent. If you're a left to right person, which I am, that's how I draw, then I go that way, and I hopefully get all of my things popped out in the same direction. And so every once in a while you can get things that the Y is pointing in the other direction here, but that's kind of what happens when you get all these different angles. Okay, so what we can see here are my local Y-axis is pointing up. Okay, so when I go on to look at my LBYY, I'm looking at the bending here about the Y-axis. Okay, and that Y-axis I'm going to say is going to be actually the 4 foot is going to be the purlins in and out of the page that are helping to brace that. Okay, so the other one is segment, LBZZ. So if we were thinking about LBZZ, that's going to be the bending here that are about the Z-axis here. So what we've got is I can put segment in. And I had mentioned that earlier here, but you can just type in S or segment. And what that means is it's going to go from this node here to this node. It's going to calculate that distance along that segment, and it's going to calculate the distance along every node-to-node location, and that will become a brace point. Okay, so segment's a really good tool when you have something where you have to calculate it along the distance here, like on a truss. LComp top, okay, that's going to be bracing the top of the member. What we noticed was the top was where the little Y is pointing. The bottom would be down here. Okay, so if this is just a wide flange, it's pretty easy to sort of understand. The top of the member is going to be on that Y upward portion of that. When I double click on this, I can see that LComp top was going to be 4, and that would be the purlins there. Again, they're bracing maybe my top flange of that. If I'm talking about purlins, or I'm talking about maybe even the deck, if maybe we're not putting purlins in. If it was deck, I would say how often am I welding that deck down to the top chord, and that would be my spacing of that location. And then my bottom chord, LComp bottom there, is going to be just every time I frame in here with a web, that's going to help me brace at the LComp bottom. Okay, I don't have any K factors in this one right here, but let me show you a different spot where we can adjust the K factors. So if I say OK, you can adjust all this information, right, per member. So I can double click on the member and I can adjust it in here. Now, as I mentioned earlier, you've got, if we were going to be telling the program here, this one member has LComp, we did LBYYs and LComp tops and bottoms in here, we would also have to do that for the segment portion. So maybe not for the segment. If I clicked on this one here, wherever we had put segment, we wouldn't need to do that because that defaults as the full length of the member. If we look at the full length of this member, it's 4.807, okay, feet. So we wouldn't have to tell the program segment. We could leave that blank, and that would be the full length there. But we would have to tell it LBYY is 4 feet, and we would have to tell it LComp top is 4 feet for every time the purlins were going to come in. Okay, and if we were going to tell the program that possibly it wasn't braced for the whole distance, we would have to tell it from the whole distance and enter that directly in from here to here, which we could find out by clicking on F5 to find the distance tool. and coming up here, and at the bottom of my screen it tells me that the distance from this node to the top pitch node is 14.422. Okay, and then I would have to tell the program that this is actually unbraced for that distance. So you never really neglect unbraced length, no matter what method you use. You really are going to address it no matter what. So I'm going to open up my members spreadsheet, and I'm going to have each of one of my members listed here, and I'm going to go to my hot roll tab. And in hot roll tab here, I can see I just put in my unbraced lengths for segment, for and segment, and so I can see all that information listed there. I also can see here I have my K values. So what I can do is tell the program to fill in the K values here for me. And I can click on this little button here, there's a little triangle that pops up. And it will ask me here, do I want to do it for the selected members only? I'm going to tell it to calculate the K members for all members. And I can say OK. And I can see that the program will calculate those values for me based on the chart we had shown earlier. Okay, so now all my K values are going to be set up. I can adjust any of the other information here if I wanted to for my members there. I would have probably, if I wanted it part of a sway, I could have adjusted that there. So I'm going to close that down. Okay, so your trusses really can be entered in. That's kind of one of the things I wanted to show you here on the truss model. Let's jump back to here and let's take a look back at our presentation. So we're going to now talk a little bit about plate modeling. And one of the things for plates is that plate modeling in RISA is something that you want to get familiar with, and you want to understand good plate rules. Rules of thumb is what really comes in handy when you start using plate modeling. And the stuff I'm going to talk about is really just that, rules of thumb. You'll see that some may dictate your model more than others. So I know when sometimes people talk about, well, what size plate should I have? And when we start talking about these, there are going to be general rules about things to not exceed, or else you'll get sort of bad results, results that really are not good for your model. But there's a lot of ways that you can get bad results and even not come close to these size plate models issues. So there are going to be other rules that we're going to apply to your model that more on some models versus others. So we'll look at, let's start with size. Size really, for us here in the modeling that we're using in RISA 3D, the quadrilateral element, okay, is going to be your 4-node element that we see here up on the right. We don't want to have a length to width ratio that's any greater than 9, okay, and that really just means that you're not going to get any real skinny and long plates, like things like that. But 9, if you think about it, is pretty generous there. So you really, that's not a great, not a real stringent ratio. And then we also have the thickness to length ratio. Okay, so the thickness of your plate there vertically on this picture, and then to any length, the width or the length, either side, needs to be less than 3. And what we're trying to do there is also just not make the plates not too deep. If you need a real deep element beyond this, you're probably more in the solids range outside of the plate element side. You're going to get more drag struts happening inside of that plate element, and it's not going to behave as well as if you were using actually a solid element. For triangular plates, so our design engine is based on the the 4-node plate, but you can do triangular elements there. It's not recommended to build a whole model out of triangular elements, more as a transition. But when you use triangular elements there, you're going to also use your length to width ratio. Actually, sorry, that is for quads, this little piece here. But what we're going to do, we are going to stick with is this angle. We're going to want our angle to be not any greater than 135 degrees. And that's not a magic number. What that really is 90 degrees plus 45 degrees, the combination of those two. So we just don't really want our plate elements to be too obtuse. So when we look at like what a good model of just a rectangular shape here, we can see like a good shape. We can go forward here, we can see this is getting to be bad, and that's because that angle there is going to be kind of greater than that 135. We're going into more of a straight angle, and that's really not something that the solver's meant for. So it's starting to be a little bit bad, and then we can get something that's really ugly in here, and should sort of not be possible. You should start getting errors when this happens like this, but this is sort of an inverted shape where it just went ugly. There's things that you can try to do to trick the program, obviously, but you just don't want to. You want to try to stick with a nice safer shape like a rectangle, and then keeping your angles nice about under 135 degrees. And that's a rule of thumb to start with. The other piece is that I see a lot in models that come in here to RISA when we look at models is that plates connectivity is problems. So plates that can only transfer their forces at their corners. And I always stress this, and it's a simple thing to understand, but you just have to kind of think about it when you're drawing your model. So you can see here with this model below here, what's happening is that the plates are only going to be connecting at their nodes. So we have these top plates that are connecting, the corner and around the whole building, around this whole little wall here is actually connecting. But in the interior, we have some smaller plates. And they're really not connected at all. So when you start to put load on them, and as we see that load being applied, they just sort of fly away, okay? They're not actually connected to the nodes, to the plates next to them. So they start either just detaching or they start overlapping, all sorts of problematic things that you probably thought when you put that load there, it was getting to the surrounding plates, and really it wasn't. So if you're going to start submeshing around there, so if, for example, you need a little bit tighter mesh to represent something here in this area, then you really need to submesh the ones around it. And that's really important when you start building these plate models, is that when you start to submesh, what we call these submesh here, you want to make sure that everything is connected properly. Transitioning mesh is really important for this proper load transfer. And what we can see in this picture here, we have a square inside of a round, and what we've got there is, this isn't really super difficult. There's some tools you can use with the high-level generation tools in RISA 3D to help you get there. But all you're doing really is just transitioning from this geometry into a perfect, nice rectangular geometry inside. And the same thing happens on the round to square. You've got some odd shapes somewhere, but not everywhere. And so it's not super hard to do this type of where you're maintaining rectangular shapes most areas and just using some transitions to help you get from those odd places to other places. Okay, so but if you don't do that, obviously you can see what happens on the top portion. Rule of thumb here for also is meshing, decreasing your mesh size. So when we talk about meshing, you're going to probably start with a real big mesh. An original mesh is going to be sort of real macro, very large, and then we're going to kind of micro mesh it into something smaller. But when you're making comparisons between the two, you want to make sure that you decrease it in a uniform way. So when we compare an original mesh of a 1 plate by 2 plates, if we're going to compare that to another submesh and check our results, we're going to want to make sure we do it in a uniform way. So we're going to split this in half. So it goes from 1 plate to 2 plates down to 2 plates and 4 plates. Same thing, so we're just basically taking all of these mesh sizes and taking them in half. And then they're a good comparison when we start to look at them. And when we start making this mesh size decrease and comparing results, what we're really looking for is the rule of thumb of 10%. We don't want to change from this original mesh size to the new mesh size by more than 10%. If we start to see that we break the mesh down to a 2 by 4, and then we go even smaller than that, okay? We go to a 4 by 8, and we start to see that there's no change from the new mesh size to the 4 by 8, even the smaller mesh size, then we're actually getting really good results at that point, and we don't have to keep sub-meshing. But if you start to see more than 10% of change, and when I say change, I guess really the best is your deflected shape is sort of where I stick with. I always look at that deflected shape. And that's where I stop at there. And we can look at this here in an actual diagram. So we can see 1 by 1 plate. And what we would be comparing, like we said here, is a uniform, so a 1 by 2. This is one here by 2, and then we can break that down to a 2 by 4. And the deflection here goes from 8 inches down to 10.4 inches. Okay, that's more than we want there on percentage of change. Okay, that's more than 10% of actual change. So that would be something that we would say we need to submesh it one more time. If we break it down one more time to the 4 by 8, then we see that it's changing less than 10%. Okay, so that between these numbers, it's going down by less than 10%. I feel like this is a safe number for this to be meshed at. This is a nice mesh size. I'm not going to see, even if I break it down by another submesh, it shouldn't be changing less than 10%. It's going to be linear there. So I'm going to see lower and lower deflection, change in my deflection. So this is a good mesh to stick with. Okay, so plate meshing there is probably one of the important things there, and so when you start to dictate what the size is, the mesh change and the deflection changes might be even more important than things like size there. Or actually dealing with the results side. This is also another thing where we're going to be dealing with the results side of things. So when we're looking at the mesh here, we don't want our contours to be more than 3 colors here, or 3 contours within each plate. So a picture of that is a good picture here. What we see is that we have 2 to 3 changes of contours. We actually have 4 in here on the left one. So that means that we're looking at 4 different stratiations of color in this one plate. And then when we start to submesh, we see that actually we are even getting more fine-tuned. This is the exact same model between the two, the exact same situation. But as you submesh it, you get to more of a fine-tuned answer inside of that plate, and you can actually see that there were higher numbers. We just weren't detecting them inside of that very large plate. So when you're starting to look at maybe stress risers or things that are really tight in the area that you're working with, that plate, you will want to maybe submesh even tighter just to kind of identify this issue. If you're working maybe in steel plates, things like that, where you might be having some sensitivities around openings, this is an area where I would recommend, you want to try to make sure you really pay attention to these contours. If I'm working in concrete, for example, where I'm going to be averaging over a design strip, that might not be as important that I have this real high stress riser, because it's going to be averaged over a larger area. But it still is something to make sure you identify if that's something that you're needing to point out here, and then look at closer, is that you probably don't want to go over that many color variations in one plate for your contours. Okay, so and for results, so as we get more and more into results, it's really important to understand what your results are you're looking at. So when we look at RISA 3D there, we have 2 different types of axes. We have a local axis on the plate, and when we look at this axis, we can see it's the Y, the X, and the Z. This is the local axis for these plates here. We also have a global axis, and the global axis is always in the left corner portion of your model. You can see a little globe there with the X, Y, and Z. And we typically, on a RISA 3D model, right out of the box, you have your Y vertical up, but you can always change that, okay? But what you're looking at in your models there, it's important to note when things are going to be local axes versus when things are going to be global axes. And you'll see in the corners, let's see here, you'll see in the spreadsheets, you'll see when it tells you it's going to be a part of the local axis. So when you're looking at plate forces, you're going to be looking at the local axis of that plate. When you're looking at plate corner forces, for example. That's one of the corner forces are what happens at the corner of each plate, and that's going to be part of the global axis. And so you want to make sure you're understanding which one is which one. The same thing is when you're looking at the actual results, you want to make sure you understand if you're looking at per unit length basis. So when you're looking at the plate forces, you're going to be looking at them as a plate per unit length basis. When you're looking at your plate corner forces there, those are the total forces on the plate. And those are 2 values there that is going to make a big difference in your results if you didn't account for actually one is per unit length of that. So you want to make sure, and that's listed right in the spreadsheet. So you can see this, which one you're looking at. It'll say there per unit length or per plate. One of the things also is that this is a kind of one tool that people don't know about a lot, is that we have a lot of really great tools for plates that you may not know about that are sort of hiding in there. The automatic meshing is a great one. You can actually tell the program to submesh for you. That's a great tool to be able to submesh quickly, and it will do some smart submeshing for you. So if you had some transition areas, you can use that to help break things up. You also can do things like use our internal force summation tool. And the internal force summation tool is a real great tool. I'm going to just actually grab here. I'm going to open up a quick model and see we can open up a plate model fast to see this. I'm going to say here. So if I open this model, this is going to be just a real typical plate. It's actually a wall model is really what we're looking at. And when I look at this model here, this is all my plates, and one of the things I want to make sure we understand about this local axis, and it's why it's so important to make sure you address your local axis. If I turn my plates on, just like we had in our local axis for our members, we have local axis on the wireframe for the plates. And so I can say okay, and I can see that the plate local axis is going to be actually displayed on my screen. So when we talked about, and we see in the top left corner here, we have the global axis. So when we talked about the fact that the plates have local axes, we can see this, if I rotate this in more of an isometric view, I can see that they actually have this plate local axis is pointing up for me, so it shows me how things are drawn. Now, one of the most important pieces in your contours to make note of is that if I, by accident, change the local axis or draw things in different local axes from one side of the model to the other, the contours are drawn that way on the model based on their local axis. So if things happen where the local axis doesn't match from one plate to the next, we're going to have a bad contour design. The actual colors are going to look funny, and we're just going to end up sort of with a mismatched contour. It's not really going to do anything to your model in your spreadsheets. So you'll never really notice anything in your plate stresses because they're per plate, okay, or your plate forces because they're also per plate, okay? But what's going to happen is when you actually go to display your coloring of your plates and we look at things like the contours here and we look at anything here where we'll see anything, like for example FX, what we're doing here is we're sort of mapping this. We use 4 Gaussian points inside of that plate, and then we map those things just like an orthogonal map there. We just sort of go through and we try to map those, and now if things are flip-flopped, we won't be able to do that properly. So really, what you can do is once you draw your plate model is just take a quick perusal. Just make sure you say to yourself, okay, how does this look? And the best way I always do it is just turn my model on its side. And if I see any of the local axis is pointing in the wrong way, I can go directly to that one and take a look. And you have a quick tool in here. If you ever need to make a quick change to those local axes, you can go into your plates there, and we have something here that will actually, let me grab it, modify plates. It'll take this rotate local axis, and it will turn the plate local ways clockwise, counterclockwise, or out of plane flip. And it will just flip-flop things for you. So let's do an out of plane flip on this one for me. Okay, so you can just see I just sort of flip-flop things around, and then it will allow me to do that. Okay, not what I would want for this model here because everything was lined up properly. One of the other things that you can do is you can just, I'm going to just solve it really fast. And as I mentioned previously, we talked about the plate stresses. Okay, you can see plate stresses on this. This is the top and the bottom of the stresses there. You have plate forces. They are listed out here per foot. We see that at the top. If you ever also get confused about what you're looking at, whether it be the local or the global axis, on the bottom of our screen it says local x-axis right there. So we try to give you as many pointers about what's happening in the spreadsheet. Always on the bottom of that screen it gives you a little tip about what's happening. Okay. Oh, so one piece I wanted to show you before we get out of that too is the internal summation tool. Okay, so the one nice piece is there's a couple little tools on the side here that you may not use a lot, but it's a really great tool for plates, and that's why I don't want to get away from plates without showing you that. So if we look at the plate modeling here, there's this first one called internal summation. It looks like a little blue internal summation tool. And what we click on that, and it allows us to click anywhere on the screen on a node, and then I can click on another node. Okay, I can click right directly across, and on the bottom of my screen I see this tool that's giving me, as I scroll up and down, it gives me the force summation. And I can find it all along the whole distance of this. I'm looking at this whole model here. I have force in 1, 2, and 3, and a new global axis is actually cut with this, this cutting tool. So if I stop there, I can see that this giving me forces in the F1 direction there. So that was my shear force in this wall is 114 kips. Okay, and I've got moment calculated there at that location, and the location of the geometric center of where I cut that is at 15 feet and 15 feet high there. Okay, so that's exactly where I made a little cutting plane across this entire model. This is a new axis, 1, 2, and 3, so it is relative to how you have things oriented. So you wouldn't really want to go isometric or anything because it actually changes your results. It's the way you're viewing the model is how this tool is working. So you either want to just sort of go in elevation view or plan view of your model and then start using this internal summation tool. The other cool tool I have here is a tool that will help me display these contours better. So I can actually cut through here and see the display of these contours. It'll give me a whole representation of that, and I can even go ahead and actually go and see this in a detailed diagram of the cut I just made across that. Okay, so to do that, let me just show you that one more time. You can click on that contour button. It's going to let you click on any 2 nodes. So I can click on 2 nodes across there, and as I cut that, it's going to give me a cut across those, displaying me the contours even further. And then I can right-click and say, Contour Display Tool, I want a detailed diagram of that contour cut, and I can see that. And this is an interactive diagram. So this really helps me identify even more specifically, again, if you're looking at something in particular and you need to look at that even closer, I can get in tighter. Okay, so that's going to be some of the really nice tools that we have in place that you may not have heard of those. I'm going to, let's see here. So as we jump back into a model here, more of the model basis, one of the things, as we said here, check your local accesses, but make sure everything makes sense in your model. So this is kind of a model I got back several months ago, and it looked everything was okay. And then I see it's kind of masonry walls, wood beams, a truss system. They have the plates on top for the roof system, and it looked okay. And the user was asking me why the results just didn't seem right, and he had sort of a sense of it just didn't make sense. And so one of the first things I do is I run the model and I check the deflected shape. And that's the very first thing I do on a model that comes into support. I always say to myself, okay, let's see what's going on in here. So we might get results that seem okay. Maybe we didn't get any locked joints or we didn't get any issues. But when you start to look at the deflected shape, gosh, things are just flying off the screen. Okay, so those members, and this is just 40% magnified, so it's not really that much higher than anything, magnification. All we're really just seeing is things are not properly attached on this model. The plate members are not actually physically attached, and as they're not physically attached properly, they're just flying off and causing havoc in the model. Okay, so the deflected shape is really the first spot that I always just make sure, hey, does that deflect the way I thought it should? And that can even help you just pick up, you forgot to put a minus sign on your loading and you didn't realize it. So the other thing is just check your joint reactions. So you should have total loads equal total reactions. And so you should have a rough idea of how much load you put on that model. When you look at the total joint reactions, are they close to what you thought? If they're not, things are not going where you thought they were, okay? We actually have a nice big warning message that pops up in RISA 3D that went in about a version ago that if things are getting lost, things are going into a locked node, or if there's any load loss, we're giving you a big, big warning, okay? But this is something you should also manually check. And then understand the code check. So just if I get something that gives me under 1.0, I should check it, not just take the computer program's idea for that, right? So I want to look up in the code. Usually I pull up the code and see which actual equation governed and why. Maybe and that makes sense. Oh, okay, there is tension in that member, or that there is no tension. Why am I getting an equation that's pulling up a tension on there? So these are things that you want to just make sure you understand. It's your model, and you need to make sure that you're believing of it. When we talk about moving on here, we talk about models. We can talk about the fact that we can integrate now with a lot of different software packages. So again, it's so important that you make sure your model is accurate. But then you want to you can integrate that once you've got your model down, or if you can take a model from another program into RISA. So you can take your architect's BIM model, or you can take your own Revit structure BIM model right directly into RISA 3D or RISA Floor. If you have a CAD file, an AutoCAD file, you can bring that directly in. You have steel detailing files that you can now use, or plant design systems to use our CIS2 type file format to integrate right directly inside of RISA 3D and RISA Floor. So these are things that when you do those integrations, it is also very important that you go through and see what integrated properly. Maybe things didn't speak the way you thought they did. Maybe the geometry of one member came across, but not exactly as you would have anticipated. So it's important to make sure that you understand what's coming across for each type of format. When you use like a direct link with the API here, so with the Revit structure, you're going to get a lot of smart information. You can get loading across. You can get the members, the beams, everything can come across. But you want to make sure that, hey, that's loading you agree with. So I think loading is a great idea to bring it across, but you need to make sure in your structural model that you agree with what came over and how it's being applied there. The DXF model is not quite as smart. It's going to be more just geometry, not as fully loaded with all the information, just really the flat file of the geometry, and it'll come in as maybe a section set for you. CIS2 is a really useful tool. Again, it can bring loads across. It can do all sorts of information for more of a steel file format, and the IFC is very similar in that CIS2 type file format. So you can integrate those two. what I here just kind of reiterates the things, the geometry, the sizes, the materials, the loads, all of those things, even the end reactions can be brought across. So now you can actually carry your end reactions directly into the model, and it's kind of a really cool thing that you can carry. RISA floor can bring your from Revit structure directly into your end reactions for both your gravity loads and your lateral loads. So if you have your brace frames, things like that, you can actually get those end reactions to come right across. Then what information is vital to correctly transfer information? Member top offset. So one of the things that's important to note while you're building your model, are you building it top of steel or are you building it centerline? So in RISA 3D, we're going to be building things as centerline. In RISA floor, you're a little bit more of top of steel. You're understanding it's a floor model so that it's a building and it has like things that are lining up with the top of floor or top of steel. When you're using brace points, are they the model or the construction brace points? And then the model simplifications. So there's lots of times when I built buildings in RISA floor back out in the field, and they were simplified. There's tiny little jogs that I did projects in New York City that were just trying to work around other buildings, and there are little jogs in the wall, and I would simplify that in my structural model and make sure that then my connections came true. That doesn't happen in my RISA 3D model or RISA floor model, but that my construction drawings would have shown that. So there's a little bit of simplification there. I need to make sure that I don't send that type of simplification overriding the construction drawings. So we see here in this picture, this is going to show me a little bit more of the analytical assumption that we're doing for our braces. We're going to assume that we're doing centerline, where we're actually going to the model work point there. We're doing centerline analysis. That may be true. This is not a real steep angle, but I know as you get real steep, you'll start to see that that brace will pop all the way over and over, and that may be hard to actually come true. And Revit structure is kind of one of those things where it starts to really come off the page where you understand, oh gosh, I can't build it that way. So it's helpful for you to see that on the screen, but then, and this may be a simplification because maybe we'll actually make that connection come true where the forces do go straight to there and I don't have to worry about it. But that's one of the things where you have to use your engineering judgment to understand, is that how you properly will do it. This is a great modeling assumption of that centerline analysis, but then it doesn't quite show us the greatest line here, okay? Exactly when you draw that analytical model, this doesn't even come close. We're looking at a little big difference there. So that's something where if we're going to make the forces go through there with a connection that'll actually make that work, that's a real good modeling assumption. If we're not, then this might not be the greatest modeling assumption. Maybe we do really need to make sure that there's an eccentric load coming from this brace into the column before it gets into that beam area. So there's a lot of things. This integration here, this is kind of another point where we see that actually how do you build this, this physical intersection? Are we going to be drawing this in RISA 3D? I would probably have just drawn this as a big old X. Okay, but in Revit structure, when we started to draw it, we start to look at what's that physical intersection and how do we do that. Okay, so we actually have a great tool that went address this, and I'm going to show you that here from our blog. I'm going to just drag my screen over here so you can kind of see it. So one of the things is we've got a RISA news blog, and as I talked about educating, getting more educated, this is a great tool. It's right down here. It's called RISA News. And I'm going to just click on RISA News, and I'm going to open up our what we call RISA News here. It's a site that walks you through. If I can, let's see, grab it. It'll double click it twice there. It's going to walk us through exactly how to get to each posting there is going to show us different things. We've got technical postings, and we've got, maybe I'll just type it in here, but this should click right from there. Oh, there we go. We got RISA News. Okay, so what it's going to give us is kind of technical postings, updates about what happened in what's happening today. Obviously, we've got some. This is the webinar we're attending right now. But if we look at the brace, I'm going to just type in brace for here, so we can just see how this actually is already written up on our X bracing. And if I click on that, I see here that we have one on tension-only bracing, but I can also scroll down and I see here there's already one here on how to model X bracing in RISA 3D. So I click on that one. This one shows me what we're just talking about right now, which is what do we do when we have this X bracing and how do we model this properly in RISA 3D. And the big thing is yeah, first of all, is it 2 members? Is it 4 members? And this one here tells us that we really don't want to do it as 4 members. If we do it as 4 members, we're going to have a node there in the middle, and it's going to cause all sorts of load sharing between these braces. And so what we really want to use is more of a two-member system like this. So we have two members directly from one side to the other, pin, pin, and we have that physical members idea, and we talked about that, but the issue with the physical members only comes into play when there's a node in the middle. So as long as we don't use anything like we have called a model merge or anything that creates a little node in the center, as long as we keep that node free there without a node, there won't be any load sharing between the two braces. So you don't want to add that node in the middle, and you want to keep them as just as two, and you'll start to see here that you start to behave just on their own. Well, this is a picture here of actually what might happen if you apply self-weight. And so another issue with bracing there, especially if you do try to do a tension-only brace, you might want to keep the brace have no self-weight, so it doesn't actually have any of its self-weight applied during the load combination. So here is recommending that we actually do add another type of density called 0 so that we don't actually have any bending in those braces there. So when we see here, this blog is kind of a quick blog. Just wanted to show you that on the RISA News site you can just sort of type in there and search through the categories, or you can take a quick look at any of the different ones that have been posted during the last several months here. Okay. But one of the things here we've got, and we were looking here at Revit structure, is just exactly like that. We saw we had two beams, and that would be two braces, how I would have recommended putting it into RISA, but in Revit structure we would probably do it a slightly different way and maybe model that out. And what we might want to do also is just make sure that we don't get any load sharing there, and have maybe we'd actually detail that out separately. Okay. So from here, let's see here, who needs to know about all these assumptions? So we've made a ton of assumptions in this, just detailing of that braces. There's a huge assumptions that we made on the structural side. If we're not going to do the whole detailing of that connection there, then who's going to, and who needs to know that the assumptions we made? So the detailer, the fabricator, the contractor, all these things need to be communicated, basically. Communication is vital to the design process. So when you're making your assumptions in your model and you transfer those modeling assumptions to other partners, you need to make sure that you communicate what you've assumed. That's the most important piece in all of the, when we get to the final stages of actually erecting this, we need to make sure that everything came true. So how can you apply these theories and what we've talked about in your office today? Assign a champion for each software, and I've talked about this a little bit earlier too. But as I mentioned, it's a really good idea to have sort of your RISA expert in your office, and or your RISA, just RISA 3D expert in your office. Somebody who knows the software and knows exactly what's happening, and really dives in. And what we have here is really good technical support too. I think that's one of the things that RISA excels in, and that you can basically call us and talk to us a little bit. We're all going to be answering the phone here, are going to be engineers talking to you further about what you're doing. You can always send us your model into, so you send it to support and then pick up the phone or email us about what you're seeing and why you don't understand it, or why it you might want to understand a little bit better. Attend training specifically for your software. So as you get more and more working in any of the software packages here, but RISA 3D, we offer a training regionally. We also offer training here in California. But you attend a training. You'll learn, no matter what your level of experience, people walk away learning tons from actual hands-on training. So it's very in-depth, and it will show you a lot from what we've got in the software package. Create a list of modeling rules for your office. So if you are going to model a certain way, braces is one of those perfect examples that we just went through. If you're going to make some modeling assumptions about how you're doing your braces, it's important that everybody in your office knows that's the assumptions you're making, and that they all sort of are consistent with that. You'd hate to hand your model off to somebody and have them assume you did it a different way. Okay, so that's a really good thing to have an idea of what everybody's going to be doing in the office for their modeling. Establish what you like to transfer information to your partners. So who's taking ownership of what? We talked about that. Revit structure, again, is one of the ones I always think of when I think of who's going to own the geometry, who's going to own this, who's going to own that. Sit down with the design partners and just make sure you hammer out. If you're sharing a model, there's a lot of electronic information there, so you need to make sure that everybody understands who's taking ownership of what. And then utilize your software support with questions about modeling. Like I mentioned, our technical support is probably by far one of the best in the industry. I work here, so I know, but it really is a good resource. And so when you're building a model and you're working with your model, you want to make sure you're confident that what you're doing is what you agree with there. So you definitely feel free to contact for support with questions.